Most educational environments operate on a broadcasting assumption. The instructor speaks, the student listens, and knowledge transfers. But learning is a biological event that requires the physical modification of neural pathways. When instructional design ignores this hardware, information is frequently lost, creating a consistent gap between what is presented and what is actually encoded by the brain. To bridge that gap, we have to view the human brain as an information processing system, one governed by a severe structural bottleneck. Effective instruction requires mapping our designs directly onto the strict capacity limits of working memory. Learning is not determined by the volume of data an instructor can broadcast. It depends entirely on how we manage the narrow cognitive channel that data must pass through. In the mid-20th century, behaviorism dominated the field. Researchers like B.S. Skinner viewed the mind as a black box, focusing exclusively on external stimuli and behavioral outputs, while ignoring internal mental states. The cognitive revolution completely dismantled this view. Scholars like Noam Chomsky argued that to understand human behavior, we must examine the internal processing structures of the mind. This shift redefined learning as the active transformation of information through specific stages: encoding, storage, and retrieval. As psychologists mapped these stages, they identified rigid biological constraints within the system, processing limits that cannot be bypassed by effort alone. This history establishes pedagogy as a biological engineering problem. We are required to design instruction that fits within the brain's physical limits. To understand these limits, we use the working memory model developed by Baddeley and Hitch, which replaced the simpler, older concept of short-term memory. Working memory functions as a multi-component workspace. A central executive hub coordinates the system, routing incoming data to specialized subsystems. The first subsystem is the phonological loop, which processes auditory information and written text. The second is the visuospatial sketchpad, dedicated to processing imagery and spatial relationships. Both systems are extremely small. Research shows they can only hold roughly 3 to 4 distinct units of information at any given moment. When incoming data exceeds this capacity, the system reaches a hard physical limit. The information is permanently dropped before the brain can store it. Once working memory is overwhelmed, the mechanical process of learning stops. Retention becomes impossible, regardless of the student's motivation. Surviving this bottleneck requires cognitive load theory, an instructional framework developed by John Sweller. This model views working memory as a zero-sum game. The total capacity is represented by this bar, which must be shared among 3 different types of cognitive load. The first is intrinsic load. This is the inherent complexity of the material. While an instructor cannot change the complexity of a subject, they can control how it is sequenced. The second is extraneous load. This is the mental effort wasted on poor design. Cluttered slides, confusing instructions, and unnecessary distractions all consume capacity that the brain could use for learning. The final category is germane load. This is the productive mental work of integrating new information into long-term memory. Because working memory capacity is fixed, any increase in extraneous load directly steals capacity from germane load. When BAT design fills the container, the actual work of learning is displaced. An educator's structural goal is to drive extraneous load as close to zero as possible, ensuring the brain has the resources to perform the work of learning. We can manage this load using Richard Mayer's multimedia learning principles. A common design failure is the split attention effect. In this example, a diagram is separated from its labels, requiring the student to look back and forth to match them. This constant scanning forces the brain to hold visual images while searching for text, which quickly exhausts the visuospatial sketchpad. In Sweller's model, this unnecessary mental effort causes a massive spike in extraneous load. The spatial contiguity principle solves this by placing the text labels directly next to the relevant parts of the diagram. This integration eliminates the need for mental scanning, lowering extraneous load and freeing up capacity for comprehension. Another failure is the redundancy effect, reading a dense slide of text verbatim to an audience. Because the phonological loop processes both spoken and written words through the same channel, providing 2 identical streams of data creates a cognitive traffic jam. Effective design is not about aesthetics. It is the practice of aligning information delivery with the brain's internal architecture. When information successfully passes through the restrictive working memory bottleneck, it finally reaches its ultimate destination, long-term memory. Here, germane load is used to build schemas, highly organized networks of knowledge. A novice possesses scattered, disconnected facts. An expert possesses those same facts, but has organized them into a tightly bound geometric web. These schemas allow experts to bypass the processing limits of working memory. They can treat a massive network of information as a single consolidated chunk. This is why experts can perform complex tasks with less mental effort than novices. They have superior long-term organization, not larger working memories. We minimize cognitive load specifically to protect the brain's resources, so it can perform the difficult task of building these expert schemas. Modern learning faces a new threat in the form of digital multitasking and generative AI. The generative learning model indicates that a student must actively produce the connections between concepts themselves to form a lasting schema. When a student uses an AI to summarize a text or solve a problem, they engage in cognitive offloading, outsourcing that generative work to a machine. This creates a specific mechanical failure. When an AI generates the connections, the student's brain bypasses the germane load required for learning. Without that mental friction, internal schema construction is skipped. The student becomes permanently reliant on external tools because the knowledge was never actually encoded. Pedagogy should never aim to make learning completely effortless. The goal is to eliminate useless effort, extraneous load, so the learner can focus their full capacity on the structural work of building true expertise.